Okay, so now the next set of issues has to do with the discrete time processing of continuous time signals, and in particular, the following question. If x of c of t is band limited so that there's no aliasing in the C to D converter, and I put a discrete time system here, and then ask what is the effective continuous time system, that's basically the next step that I'm trying to answer. Now, one of the things I said is that if my input signal is not sufficiently band limited, then I'm going to get aliasing in the C to D converter, and so this overall system in general is not going to be LTI. So let me turn that statement around and ask the following question. If this is not band limited, so that in the sampling I end up getting aliasing, is it impossible for this system to be, overall system to be LTI? The answer is it's not impossible. In fact, it's very possible. In fact, let me give you a trivial example. If this system was a no-pass filter, which is, you can infer what a no-pass filter does. It passes nothing no matter what its frequency response is, which is frequency response is 0, then no matter whether you get aliasing at this point or you don't get aliasing at this point, you're going to have an LTI system. It's pretty trivial. However, the more interesting situation, and I will tell you that a lot of people don't understand this point, even though it's a pretty straightforward point to argue. If I have aliasing in the C to D converter, and if this filter discrete time system eliminates the aliasing part of the signal, then this overall system will still be a continuous time LTI system. So in fact, when you're doing discrete time processing of continuous time signals, you often can incorporate aliasing, allow aliasing in the D to C converter or the A to D converter in practical terms, if those alias components end up, in any case, being eliminated by the discrete time system. And it's just important to kind of park that point away in your mind so that you clearly understand it. Okay, now, in terms of the relationship between the overall frequency response of the continuous time system and the frequency response of the discrete time system, the relationship is a very simple, straightforward one. And rather than kind of arguing it with some algebra, let me just kind of argue it with a bunch of diagrams, and I think the argument should be pretty obvious. So here's roughly the idea. We start with a continuous time signal. Of course, we've converted to, think of it in the context of that diagram with the sampling and impulses to samples, although you don't have to think about it this way. And at first, just ignore what h of e to the j omega is here. So we've replicated the spectrum of the continuous time signal, and then to be at the output of the C to D converter, we're just normalizing the frequency axis so that 2 pi over capital T gets normalized to 2 pi. So we're at this point. Now we go through the discrete time system, and I've drawn it here assuming that the discrete time system is an ideal discrete time low-pass filter, but it can be anything. What are we doing? Well, we're basically, at that point, we're multiplying the discrete time spectrum by the Fourier transform of the filter. And then we take that product and we just now go through the D to C converter. As we go through the D to C converter, well, so we multiplied the spectrum of the discrete time signal out of the D to C converter by this rectangle. So now we end up with something like this. And then we back our way out, and there are two steps that you could think of in terms of backing our way out. One is to unnormalize the frequency axis. So 2 pi gets unnormalized to the sampling frequency, 2 pi over capital T. And then what we do is extract the baseband replication. Now, don't get confused about the 2 different low-pass filters that are involved here. There's one that is this rectangle that I have here that is what h of e to the j omega is, and then somehow where I've extracted this baseband spectrum. Now, if we go back to this picture, where is that low-pass filter? Where is the low-pass filter that is, so the rectangle that I've been showing, that's this rectangle. Where is the low-pass filter that is extracting this? Or asked another way, does this signal, or the time function that corresponds to this spectrum, ever show up any place in that diagram? It would show up if I interpreted the D to C converter in terms of this picture, because that would be sitting here. And then I've got the low-pass filter. So a question that often comes up in 341, so let's just nail it right now, is that the low-pass filter is part of the D to C converter. Because, in fact, what I'm saying is I'm doing band-limited interpolation. It's that band-limited interpolation that is extracting out this baseband replication. If you think of this whole picture, it then pretty much tells you, if I think about what the effective frequency response is of the continuous time filter that is sort of end-to-end in that system. So what are the steps that happen? So one step that happens is this is just going to be h of e to the j omega, but with omega capital T equal to little omega, or capital omega equal to little omega over capital T. And then we're done. Right? Wrong. So I'm still adjusting. I like throwing these questions out and then getting answers back, but now with the clickers, I'm saving you the agony of my saying, right? And then making direct eye contact. Okay, well, this is not quite right, because this picture would be sitting here. So now we have to do the low-pass filtering. Well, that's easy for me to do, because this is what it is for the magnitude little omega less than pi, or capital omega less than pi over capital T, and it's equal to 0 otherwise. I just did the low-pass filtering. That's what I did by writing that down. Easier to build a low-pass filter with the chalk than it is to actually build one in the lab, I guess. Okay, so here's where we are. You said, let's assume that my input signal is band limited. I go through the C to D converter. I go through a discrete time system, which is a low-pass filter. And it's a low-pass filter with this cutoff frequency. And the overall system then has an overall effective frequency response. So the question I'd like you to think about is what the equivalent cutoff frequency is of the overall equivalent continuous time low-pass filter.